Units and measurements is the first chapter of the physics, and in units and measurements the topic 1 we are dealing with the topic 1. Topic 1 is physical quantities are of three types. There are three types of physical quantities, and the first one is fundamental or basic quantities, second one is derived quantities, and the third one is supplementary quantities. Fundamental or basic quantities, derived quantities, and supplementary quantities are the three types of physical quantities. And firstly, we are dealing about fundamental or basic quantities. In fundamental or basic quantities, it can neither be derived from one another. That is, it cannot be derived from other quantities. Okay, it's fundamental in nature that it cannot be derived from other quantities, and it cannot be divided or resolved. Okay, it cannot be resolved into smaller units. This is fundamental quantities, this is basic quantities. This is cannot be resolved into smaller quantities, and it cannot be derived from one quantity, and it cannot be resolved into smaller quantities. And the examples are meter. It cannot be derived from other quantities, and it cannot be further divided into other quantities, right? Kilogram, second, are the examples. And then second one is the derived quantities. We are talking about derived quantities. Derived quantities are derived from fundamental quantities. These are derived from the fundamental quantities. And here the examples are meter per second, kilogram meter per second square. This kilogram meter per second square is also known as Newton. Newton is also known as kilogram meter per second square. Here, these derived quantities are derived from fundamental quantities, and it can be resolved into smaller quantities. That it means meter per second is again resolved into meter and second. Okay, meter per second, it has two units, meter and second. Kilogram meter per second square has three units, kilogram, meter and second square, right? Kilogram meter per second square has three units, kilogram, meter and second square, right? Okay, this can be further divided or resolved into smaller units, and it is derived from fundamental quantities. And the third one is the supplementary quantities. Supplementary quantities. In supplementary quantities, we are going to learn about two quantities, that is plane angle and solid angle. Plane angle means it is the angle subtended at the center of the circle. The angle subtended at the center of circle by an arc of length. This is the arc length. This arc length is equal to the radius. This is the radius and this is the arc length. Arc length is equal to radius. At that time, the angle subtended will be equal to the plane angle. Solid angle is in the case of sphere. And in the case of solid angle, the unit is radian. The important thing is we have to learn about the plane angle, the unit is radian, and in the case of solid angle, the unit is radian. So, firstly, we are learning about the three types of physical quantity: fundamental or basic quantity, derived quantity, and supplementary quantity. Fundamental or basic quantity means it is fundamental in nature, that is, cannot be derived from other quantity, and it cannot be resolved into other quantities. Derived quantity means derived from the fundamental quantities, that it can be resolved into further quantities, further units. Supplementary quantity. In supplementary quantity, we are dealing with two types of quantity, plane angle and solid angle. Plane angle, in plane angle, the unit is radian. Solid angle unit is steradian. Okay. And then we are dealing with topic 2. Topic 2 is units. What is units? The magnitude of physical quantity can be represented as m is equal to nu. This is the magnitude. Magnitude is equal to nu. In this case, the n is the numerical value and the u is the unit of that quantity. So, for example, when we are talking about distance can be represented as 10 meter. In this, 10 is the n. 10 represents the numerical value, and the meter represents the unit. Meter represents unit, and 10 is the numerical value. That is, 10 meter is equal to nu. Every quantity, every physical quantity's magnitude can be represented as nu, and here n is the numerical value and u is the unit. Here n represents 10 and m represents the meter. Then we have to learn these. Smaller the unit, greater will be the numerical value. That is, if unit is smaller, the numerical value, that is n is inversely proportional to u. This is very important. N is inversely proportional to u, and that is nu is equal to constant. Nu is equal to constant, that is n1 u1 is equal to n2 u2. Smaller the unit, if unit is smaller, if this is the unit is smaller, numerical value will be largest. So, for example, we have to consider the 100 centimeter and 1 meter. We know that 1 meter is equal to 100 centimeter, right? So, here in this case, 1 meter is equal to 100 centimeter. The 100 is the larger quantity and 1 is smaller quantity. Centimeter is the smaller quantity and meter is the larger quantity. So, inversely proportional, right? When the numerical value is small, the unit is large, and numerical value is large, unit is small. That 100 is large, 1 is small, centimeter is small, meter is large. 100 large, centimeter small, 1 small, meter large, right? Meter is large than centimeter, right? So numerical quantity of meter, that is 1, is smaller than numerical quantity of the centimeter, that is 100. So this is topic 2, and here we have to learn that n is inversely proportional to u. n1 u1 is equal to n2 u2. This is the important relation on this topic 2. And when we are moving on to the topic 3 is about the classification of units. Units are classified into four systems of units are there, and the first one is the CGS, and second one FPS, third one MKS, and the fourth one is SI system. First one is CGS, means C represents centimeter, G represents gram, and S represents second. Centimeter, gram, second, and centimeter is used to denote length, mass, gram, time, second. In CGS system, the length, mass, and time is measured in this. Length is measured using the unit centimeter, mass using gram, and time to represent time we use second. Okay, and centimeter, gram, second is the first one. Second one FPS, that is length, mass, time, foot, pound, second. Foot, pound, second is the FPS system. MKS system, here meter, kilogram, second. Meter for representing length, kilogram, mass, second for representing time. And the fourth one is the SI system. This is very important. SI system, for representing length we are using meter, mass for kilogram, time for second, and electric current ampere, temperature Kelvin, amount of substance mole, luminous intensity Candela. Length meter, mass kilogram, time second, electric current ampere, temperature Kelvin, amount of substance mole, luminous intensity Candela. So these are the four system of units. First one is CGS, centimeter, gram, second. Second one foot, pound, second. Then third one meter, kilogram, second. Then comes the SI system, length meter, mass kilogram, time second, electric current ampere, temperature Kelvin, amount of substance mole, luminous intensity Candela. SI system is very important. We have to learn these all units. So then comes the fourth topic. Fourth topic is about dimension. Dimension means power to which base quantity is raised to represents the quantity. Power to which the base quantities are raised by some powers. Okay, to represent the quantity, base quantities like mass, length, time are raised to powers. Base quantities like mass, length, time are raised to some powers to represent the quantity. Okay, so we are dealing with dimensional formula of mass. In the case of mass, we use m raised to 1, L0, T0. Mass, m raised to 1, L0, T0. And speed, distance divided by time. Distance, length divided by time, T. So, m0, L1, T. When it comes to the numerator, T raised to -1, right? L1, T raised to -1, speed. Dimensional representation, for mass we use m, length L, time T. Okay, mass m, length L, time T. And some dimensional formulas. Force is equal to mass into acceleration, that is mass we use m. right? Acceleration is equal to velocity divided by time. Velocity divided by time is acceleration. Acceleration velocity means here we have written that LT raised to minus 1. Okay, that is LT raised to minus 1 divided by T raised to 1. When it comes to numerator, LT raised to minus 2. Okay, LT raised to minus 1 divided by T raised to 1. LT raised to minus 1 divided by T raised to 1. When it comes to the numerator, it is like LT raised to minus 2. Mass for mass m, and acceleration velocity divided by time, LT raised to minus 1 divided by T, which is equal to LT raised to minus 2. Okay, and then density is equal to mass divided by volume, m divided by L cube. So here m, LT raised to minus 2 is the unit of force. Okay, and density, mass divided by volume, m divided by L cube is equal to ml raised to minus 3. And then power, work by time. For work, force into displacement, force, we have found that mlt raised to minus 2 into L, that is ml square into T raised to minus 2. ml square into T raised to minus 2 divided by T is equal to ml square T raised to minus 3. For pressure, force divided by area, ml T raised to minus 2 divided by L square m. So when L square comes into numerator, that is L raised to minus 2, it will become m L raised to minus 1 T raised to minus 2. Angular displacement, theta is equal to arc divided by radius, arc length and radius L, that is it is dimensionless, m0 L0 T0. Angular velocity, theta divided by time, that is m0 L0 T raised to minus 1. And angular acceleration alpha is equal to omega divided by T, that is omega, the unit is T raised to minus 1 divided by T is equal to T raised to minus 2. And in the case of torque, force into perpendicular distance, mlt raised to minus 2 into L, that is force into perpendicular distance, that is mlt raised to minus 2 for force, and perpendicular distance L, ml square T raised to minus 2. There are also some other cases. We can deal with it when we are going into later chapters, right? Then comes the principle of homogeneity. Principle of homogeneity means in an equation of addition and subtraction, we have the equation x plus y is equal to z. This is an example of addition equation, and a minus b is equal to c is an example of subtraction equation. Here the dimension of every term is equal, that is dimension of x is equal to dimension of y is equal to dimension of z. Also dimension of a is equal to dimension of b is equal to dimension of c. We have to note that it is in the case of addition and subtraction, the dimension of each term will be equal, that is dimension of each term means x, dimension of y is equal to dimension of z, dimension of a is equal to dimension of b is equal to dimension of c in the case of addition and subtraction. That here comes an example, v is equal to u plus at. The first term will be v, dimension of v is equal to second term u, dimension of u is equal to third term will be at. V, dimension of v is equal to dimension of u is equal to dimension of at, which will be lt raised to minus 1. Okay. And then in case of multiplication and division, the dimension of LHS is equal to dimension of RHS. Left hand side, the dimension of left hand side will be equal to dimension of right hand side, that is dimension of A into B will be is equal to dimension of C, and dimension of A by B is equal to dimension of C. Okay, dimension of A multiplied by B will be equal to C, and dimension of A by B is equal to C. That is dimension of LHS is equal to dimension of RHS. And but in case of addition and subtraction, dimension of each term will be equal. In case of multiplication and division, dimension of LHS is equal to dimension of RHS. And here speed equal to distance divided by time, dimension of speed equal to dimension of distance divided by time. Okay, and then next one is uses of dimension. first use is to check the correctness of equation. If equation is correct or wrong, we have to check that using the dimension. If dimension of LHS is equal to RHS, equation may be correct. Equation may be correct. If dimension of LHS is not equal to RHS, equation must be incorrect. Okay. If dimension of left hand side equal to right hand side, equation may be correct. If dimension of LHS is not equal to RHS, then equation must be incorrect. And here comes an example. Force is equal to ma, that is mass into acceleration. Force, we have already found that the dimension will be force m lt raised to minus 2, that is m into lt raised to minus 2, and here m and a dimension of a is equal to lt raised to minus 2. So the dimension of left hand side equal to dimension of right hand side, so equation may be correct. So when we are dealing with another example like centrifugal force, Fc is equal to mv square divided by r. Okay, for we know that Fc, centrifugal force, is equal to mv square divided by r. The dimension of force is equal to mlt raised to minus 2 is equal to mv square divided by r. The dimension of mass is equal to m, and dimension of v, that is velocity, is equal to lt raised to minus 1 divided by Fc is equal to mv square. Sorry, we can write with this. Centrifugal force is equal to mv square divided by r. So the centrifugal force has the dimension, we already know that mlt raised to minus 2 is equal to, the dimension of mass will be m, and v square, v has the dimension lt raised to minus 1 whole square divided by l, right, which is equal to ml square t raised to minus 2 divided by l. Here comes the equation mlt raised to minus 2, that LHS is equal to RHS, right? LHS equal to RHS. This is the another example. Centrifugal force. Example of centrifugal force. Then this is the first use to check dimensional correctness of equation, and the second use will be to convert a physical quantity from one system of units to another. That we know that in the case of length we have so many system of units like meter, centimeter, millimeter, right? In the case of mass we have kilogram, gram, right, pound, like these. So in case we have to convert one system of unit into another, that is we have already studied about system of units like CGS, FPS, MKS and SI system. So first we have a question like convert SI unit of force to CGS unit. SI system, the force has the unit Newton. Newton means kilogram. We already studied that kilogram meter per second square is Newton, kilogram meter per second square. And CGS unit we are saying dyne. Dyne means equal to gram centimeter per second square. Okay, CGS means centimeter gram second, and SI unit means kilogram meter per second. Newton is equal to kilogram meter per second square. CGS unit dyne is equal to centimeter gram per second square. Okay, and then we already knew the equation that N1U1 is equal to N2U2, right? N is inversely proportional to U, that is NU is equal to constant, N1U1 is equal to N2U2. So we have to find that 1 Newton is equal to how many dyne. 1 Newton is equal to how many dynes. Okay, how many dynes. So Newton, kilogram meter per second square means kilogram meter second raised to minus 2 is equal to, we don't know about how much it is in CGS unit. So we are putting it as N2 gram centimeter second raised to minus 2. So we are equating it and when we are bringing it into left hand side, it will go into the denominator like this: kilogram divided by gram, meter divided by centimeter, second raised to minus 2 divided by second raised to minus 2. Here we can cancel second raised to minus 2 divided by second raised to minus 2, which is equal to n2, right? So we know that 1 kilogram is equal to 1000 gram, right? We have to equate in this. In place of kilogram, we have to write 1000 gram. Kilogram is equal to 1000 gram divided by gram. Meter, in case of 1 meter, we have to write 100 centimeter divided by centimeter equal to second raised to minus 2 divided by second raised to minus 2, which is
divided by second raised to minus 2, which is equal to n2, which will be equal to 10 raised to 5, that is gram, centimeter, second raised to minus 2, second raised to minus 2. 1000 into 100 will be equal to 10 raised to 5, which is equal to n2. So once more, 1 Newton is equal to how many dyne? 1 Newton means kilogram, meter, second raised to minus 2, which will be equal to n2 gram. Dyne means gram, centimeter, second raised to minus 2. When gram, centimeter, second raised to minus 2 comes into RHS, it will be in the denominator, right? So we have to equate 1 kilogram as 1000 gram, 1 meter as 100 centimeter, and second raised to minus 2 as second raised to minus 2. We can cut this, and 1000 gram, we can cut gram, and centimeter. 1000 into 100 will be equal to 10 raised to 5, right? And 2 will be 10 raised to 5. That is 1 Newton equal to 10 raised to 5 dyne. Okay. And then third use will be to derive relationship between different physical quantity. To derive relationship between different physical quantities, that is time period of a simple pendulum. Time period of a simple pendulum. Time period of pendulum depends on length, acceleration due to gravity, g. Okay, time period depends upon the way. In the question, it's given that in which of the following quantities the time period depends on which of the quantities, right? In the question, it's already given that time period of pendulum depends on length, acceleration due to gravity. Okay, so we can say that dimension of time period is equal to t, dimension of length is equal to L. We already know that dimension of acceleration is equal to Lt raised to minus 2. So dimension of acceleration due to gravity is also will be Lt raised to minus 2. First of all, we have to write the time period of simple pendulum and the time period depending quantities like dimension of length L, dimension of acceleration due to gravity G is equal to Lt raised to minus 2. So we can write as time period will be depending on length and acceleration due to gravity, that is T will be proportional to length. We don't know to which power will be length depending on, so we can write as T is proportional to L raised to A, that is dimension of length, and G raised to B, okay, acceleration due to gravity raised to B, that is T is proportional to L raised to A, and the dimension of acceleration due to gravity is Lt raised to minus 2, Lt raised to minus 2 whole raised to B. Okay, T is proportional to L raised to A and L raised to B here. So we can write it as L raised to A plus B into T raised to minus 2B. Okay, minus 2 and B. Okay, T raised to minus 2B when it comes to when we open the bracket. Okay, upper T is proportional to L raised to A plus B and T raised to minus 2B. Here we know that L raised to 0. Here in the left hand side there is no L, so we can consider it as L raised to 0. So we can take it as A plus B will be equal to 0, that is L raised to 0, T raised to 1, L raised to 0, T raised to 1 will be proportional to L raised to A plus B. So we can equate this. A plus B is equal to 0, A plus B equal to 0. So A is equal to minus B. So, and in this case, T raised to 1 is equal to T raised to minus 2B. But 1 is equal to minus 2B. That is minus 2B is equal to 1. B is equal to minus 1 by 2. A plus B is equal to 0. A is equal to minus B. So, A will be plus 1 by 2. Okay. T is proportional to A. L raised to A, that is L raised to A, that is L raised to plus 1 by 2, and G raised to B, that is B is equal to minus 1 by 2, G raised to minus 1 by 2. T is equal to, we can remove this proportionality constant by adding a dimensional constant, that is 2 pi. So in the limitations of using dimension, we will study about there is no mentioning about this dimensional constant. Okay, we are supposing it, we are by through solving problems we are using it as 2 pi. We found that it is 2 pi, and through to derived different relationship between different quantities, there is no mention about we cannot find the dimensional constant, we only find this relationship. Okay, this is dimensionless constant. Dimensionless constant means there is no dimension, this is a number. Okay, so there is no dimension for this, so we cannot find that. Okay, as so T is proportional to L raised to 1 by 2 and G raised to minus 1 by 2. T is equal to 2 pi into root of L by G. Limitation of dimensional analysis is the next one. It doesn't give information about some numbers, that is, this is dimensional constant, dimensionless constant. Dimensionless constant. It is not giving any information about this dimensionless constant. Any information about this some numbers, or that is dimensionless constant, it doesn't give information about this dimensional constant, it only give information about L and G. Okay, and then second one is, it is useful only when quantities related by multiplication and power relation. Okay, if it is related by multiplication, F is equal to MA, and power relation, like root of L by G, it fails for the quantity that depend on the sum or difference, that is S equal to UT plus half AT square. UT plus half AT square, we cannot find this relation using dimensional analysis. Okay, we cannot find this relation as there is these two terms are related by sum. When the two terms are related by sum or difference, we cannot find that relation using dimensional analysis. We can only find the quantities related by multiplication and power relation. We cannot find it using sum or difference. Okay, and the next one, this is all about dimension. We have studied that dimension of some quantities, and then principle of homogeneity in case of addition and subtraction. Dimension of every term will be equal, multiplication and division. Dimension of LHS is equal to RHS, and then uses to check correctness of equation, to convert a physical quantity from one system of unit to another, and to derive relationship between different quantities, and to derive relationship between different quantities. The dimensionless constant, we cannot find the dimensionless constant, we can only find this proportionality. Okay, and then limitation doesn't give information about some numbers, that is dimensionless constant, and then we can only find the relationship of quantities related by multiplication and power relation. We cannot find, it fails for the quantity that depend on the sum or difference. Okay, and then next one is the error analysis. Error. We can study the error measurement using a an example. Okay, first one is measured length of rod. When we measure the length of a rod, okay, we get the length as L1, L2, L3 and L4. Okay, we get different length. Okay, and if the question is to find the true value of rod, it how we can find that? We have to find the L mean. That is, we have to add these quantities, that is L1 plus L2 plus L3 plus L4 divided by number of quantities. That is, here we have 4 quantities, that is divided by 4. So if the question is to find the true value of rod, we have to find the L mean. L mean by L1 plus L2 plus L3 plus L4 divided by 4. Second is to find the absolute error. Absolute error means, here true value of rod means L mean. Here absolute error means delta L mean. Delta L mean. Okay. True value of rod means L mean and absolute error delta L mean. For delta L mean, we have to find delta L1 plus delta L2 plus delta L3 plus delta L4 divided by 4. So how we can find the delta L1? Delta L1 means modulus of true value, that is L mean minus L1, and delta L2 is equal to modulus of true value, that is L mean minus L2, and delta L3 is equal to L mean minus L3 modulus, and delta L4 is equal to modulus of L mean minus L4. Okay, so we can find delta L1 as modulus of true value minus L1, delta L2 as modulus of true value minus L2, and delta L3 as modulus of true value minus L3, and so on. So delta L mean is equal to delta L mean is equal to delta L1 plus delta L2 plus delta L3 plus delta L4 divided by 4. So relative error means absolute error divided by true value, that is absolute error delta L mean divided by true value means L mean. Delta L mean divided by L mean. Percentage error means relative error into 100, that is delta L mean divided by L mean, that is absolute error divided by true value L mean into 100%, we get percentage error. Error propagation in mathematics, when we add some quantities, there is propagation of error. So when we have a physical quantity having true value x and y, absolute error is delta x and delta y. Suppose we have two rods. First rod measure is x, and the absolute error in it is delta x, and second rod measurement is y, absolute error is delta y. Suppose we have to add these quantities. Okay, we have to add the length of rod, that is x plus y will be equal to z. Okay, x plus, we have two rod. First rod we have x is the true value, x is the measurement of rod, and delta x will be the error in the measurement of the length of the rod. And in the second rod we have the measurement y, and delta y will be the error in the measurement of the length of the rod. Okay, when we are adding these two length of these two rods combinedly, we get x plus y equal to z, that is the true value x and y, x plus y is equal to z. So when we are measuring the propagation of error, that is the error in the first rod is delta x and error in the second rod is delta y. So total error will be delta z is equal to delta x plus delta y. Okay, delta z is equal to delta x plus delta y. This is the combined length of the rod, and delta z, this is the error in the first rod, error in the second rod. The total error will be delta z is equal to delta x plus delta y. And when we are subtracting the length of rod. Okay, this is the first rod and this will be second rod. When we are subtracting, this is length x, y, delta x is the error and delta y is the, when we are subtracting it, we get this is z, this as z. When we are subtracting, it will be z, x minus y is equal to z. So the error in the rod 1 will be delta x and the error in rod 2 will be delta y. So total error in this measurement will be also delta x plus delta y. So in case of addition or subtraction, total error will also be delta x plus delta y. Total error in we have to add the total error. Okay, we have to add the total error. Delta z is equal to delta x plus delta y. Here in the case of subtraction also, total error will be delta x plus delta y, the error in first rod plus error in the second rod. Okay, and in case of multiplication in case we have to find this is the relative error, delta z divided, this is the first rod, and if we are finding the area, right, this is the first rod and this is the second rod, we have to find the area together. We have to, this is a rectangle, in rectangle this is the length and this is the breadth, this is the length, this is the breadth. So we know that x into y will be the area. Okay, the measuring, in measuring the length, in measuring length will be y, right? The error in measuring length will be delta y. We get an error of delta y in measuring length and we get an error of delta x while measuring the breadth of the rectangle. So total error we have to find that here we are finding the relative error. To find the relative error, delta z divided by z will be equal to delta absolute error divided by true value plus delta y divided by y. Okay, delta z divided by z is equal to delta x divided by x plus delta y divided by y. So here we have an example, right? This is a rectangle. This is a rectangle, and in case of rectangle, we have the length y. We are measuring the length y here, and we are measuring the length breadth as x. While measuring the length, we get an error of delta y. While measuring the breadth, we get an error of delta x. And we have to find the area. Area is equal to x into y. So we get the area, but there will be some error in measuring area, right? We get a error in measuring the length and we get an error in measuring breadth, right? So the error will be equal to, how to find the error? Here we are finding relative error. Relative error will be equal to, in measuring the area, x into y is equal to z. Z will be area. Delta z, total error in area divided by true value of area is equal to delta x divided by x first term into second plus second term, delta y divided by y. Okay, relative errors, we have to add the relative errors of each term. So if we have to find the absolute error is equal to delta z. Delta z is equal to delta x divided by x plus delta y divided by y into z. Okay, this is the absolute error and this is relative error. Okay, And in the case of division, this is in the case of multiplication. In case of addition and subtraction, error is delta x plus delta y, delta x plus delta y. And in case of multiplication and division, delta z divided by z is equal to delta x divided by x plus delta y divided by y. And here also delta z divided by z, this is will be answer. Delta z divided by z is equal to delta x divided by x plus delta y divided by y. Okay, and then here is an example. Z is equal to 3x. Delta z divided by z is also equal to delta x divided by x. We don't consider about the term 3. Okay, we don't consider about 3 because it is a numerical value, right? So delta z divided by z is equal to delta x divided by x. Okay, and then z is equal to x cube when it comes into power. Okay, z is equal to x cube. Delta z divided by z is equal to 3 into delta x divided by x. Okay, delta z by z is equal to 3 into delta x divided by x. T equal to 2 pi into root of L by G. Root of L by G means L by G whole raised to 1 by 2. Root of L by G means L by G whole raised to 1 by 2. So L by G whole raised to 1 by 2. 1 by 2 comes here. Delta T divided by T is equal to 1 by 2 into, we don't consider 2 pi, 1 by 2 into delta L divided by L plus 1 by 2 into delta G divided by G. We don't consider 3, so we don't consider 2 pi. L by G, we have to consider L by G. L by G whole raised to 1 by 2, right? So 1 by 2 into delta L divided by L plus 1 by 2 into delta G divided by G. So this is the end of error measurements. Okay, and then significant figures. Significant figures, there are some rules to find the significant figures, number of significant figures. Okay, so first rule is all non-zero digits are significant. That is 1, 2, 3, 4, etc. All non-zero digits are significant. Second one, all zero between two non-zero digits are significant. That is when 1, 0, 0, 1 between two non-zero, 1 and 1 are two non-zero digits, there will be 0 in between two non-zero digits. So total number of significant figure in this will be 4 significant figures. Okay, and then when the question is 0, 1, 2, and here 0 is not in between two non-zero digits, so here the significant figure will be 2 significant figures. If 0 is in between two non-zero digits, the 0 will be significant. That is 4 significant figure. Here the 0 is not significant. Here the 0 is not significant. Here the zeros are significant because it is in between two non-zero digits. So total 4 significant figures. Here there is only 2. That is zeros to the right of decimal point are significant. So here it is saying that 2.00. So here in 2.00, the 2.00, there will be 3 significant figures. 3 significant figures. 2.00. There is a non-zero digit before decimal point, so there will be 3 significant, so the zeros are significant, so there will be 3 significant figures. That is, in this case, in the number less than 1, that is zeros behind this, that is 003. Okay, if also there will be a decimal point, 0.01, 0.0101. In this case also if in this case these zeros are not significant, only 3 is significant, and in this case these zeros 0.0 is not significant, only 101 is significant. Here we have only one significant figure and here we have only 3 significant figures. Okay, and then the terminal zeros in a number without a decimal point are not significant. That is 2 0 0 0 0. Here the terminal zeros without a decimal, there is no decimal point here, so there will be only one significant figure, that is 2, and the power of 10 is irrelevant to the determination of significant figure. If we have 7.05 into 10 raised to 12, here we have only 3 significant figure, that is 7.05 will be significant, this 10 raised to 12 is not significant. Okay, so the cases are zeros between two non-zero digits are significant, here 4 significant figure, zeros 0.12 0 1 2 0 1 2, the zeros between two non-zero digits are significant, and if the zeros are not in between two non-zero digits, it's not significant figure, here only 1 2 are significant figures, so 2 significant figures. So zeros after a decimal point, if zeros after decimal point, and here we have a non-zero digits like a number greater than 0. Okay, so here 1.00 there will be 3 significant figures, these zeros are significant figures, that is after decimal point the zeros are significant figures. We here we have a non-zero digit, right, and here we have a 0 after decimal point, but we don't have a non-zero digit here, so these two zeros are not significant, and 101, that is zeros between two non-zero digits are significant. Here there is no decimal place, so these 3 will be only significant, so here we have only one significant figure. The terminal zeros without a decimal point, there is no decimal point in this place, so these all zeros are not significant figure, only 2 will be significant. The power of 10 is irrelevant, it is not significant, so 7.05, only 3 significant figures. In case of addition and subtraction, 24.36, 0.0623, 256.2. In case of addition and subtraction, we have to consider number of digits after the decimal point. Here we have 2 digits, here we have 4 digits, and here we have 1 digit. Okay, 1 digit. Okay, and the answer should contain least number of decimal places, that is we have in the answer we have only 280.62223 is the real answer, so answer should contain only one significant figure after the decimal place, so that is least. Here 1 is the least significant figure, here we have 4 digits, here we have the total significant figure in 24.36 will be 4, and here we have total significant figure will be 3, and after decimal places there will be 2 digits in this, and there will be 3 significant figures in this, and here we have one significant figure, so this one significant figure we have to consider, and the answer should contain this one significant figure, that is 280.6 will be the answer. And in the case of multiplication and division, we have to consider the least number of significant figure. Here we have to consider the significant figures after the decimal place, but in multiplication and division we have to consider the total significant figures. 2.80 we have 3 significant figure, 4.503 and we have 5 significant figure. So the real answer is thus, but the answer should contain the least number of significant figure, that is 3 significant figures, that is 12.6. And here we have in addition and subtraction we have to consider only the significant figures after the decimal place, that is here 2 significant figure, here we have 3 significant figure, here we have 1 significant figure. So in the answer should also contain the least number of significant figure after the decimal place, that is 1 significant figure. But in case of multiplication and division we have to consider the total number of significant figure, 3 significant figure, here we have 5 significant figure. So the answer should contain 3 significant figure, that is total 12.6.